Okay, so we discussed rolling, all right, but now we want to look at exactly some of the forces and torques involved in rolling. Okay, so here I have a block and a ball, okay, they're at the top of an incline, and I'm going to release them both from rest, and this is frictionless, okay, and I want to know which object reaches the finish line down here first, okay. Well, first of all, if it's frictionless, the ball's not going to roll, okay. So the ball and the block are just going to slide down together, okay. It's going to be a tie, right? There's no rotation. So we know that when you've seen a ball roll down an incline, what force causes the ball to roll down the incline? Okay, so now we're going to draw these pictures we haven't drawn before. So here's the ball, okay, rolling down the incline, right? And I drew the forces that acted on the ball. Okay, now again, the ball rolls because the incline is rough. Okay, there's friction. So I drew the forces that acted on the ball. So I had the weight, okay, had normal force, all right, and static friction. Okay, so it's no surprise because if we had a block, okay, that was the direction of static friction because the block is trying to go down, the incline. Okay, here, static friction is what causes this thing to roll. Okay, so I think we saw a video before that when I have a disc on the table, okay, or a ball on the table, and I'm pulling a piece of paper, okay, as the paper gets pulled away to the left, that acts like a static friction force, which causes it to rotate in that direction. That's exactly what that thing looks like it's doing. Okay. Okay. Now, much earlier, all right, I talked about that when you draw your force diagrams, okay, right, so here was a block on an incline, there's your mg, there's your normal force, points perpendicular, there's static friction, okay, that's not good, right? You really have to draw the forces where they act. And that's important now, especially we're going to look at torque, because you have to draw the forces exactly where they act so that you can measure them with respect to an axis of rotation, okay? So here I was really careful to draw the forces where they act. So the weight acts at the center of mass, normal force is going to pass right through the center of mass, that's the axis of rotation, and static friction is acting right at that contact point. Okay, so if I look at what forces cause a torque, okay, remember, torque is force times moment arm, okay? Normal force passes the axis of rotation, has no moment arm, causes no torque. mg passes the axis of rotation, also does not cause a torque. So the only force that causes a torque is static friction. So static friction causes, in this case, a clockwise torque about axis A. So static friction is what causes this thing to roll, all right? And this picture over here, okay, this one over here, this was frictionless, so the ball would not rotate. It would do the same thing as the block and just move as a point mass down the incline. Okay, now, here's two different situations, okay? Here I have a bowling ball, okay, and I have a little thing drilled into the bowling ball, and I have a string, okay, a little bolt, and I have a string attached to that, and I'm going to pull the bowling ball. So this force, okay, my pulling force, okay, passes through the axis of rotation, okay. So that pulling force acts through the axis of rotation, so that pulling force doesn't cause a torque because there's no moment arm, okay. So that means this pulling force is not going to cause a rotation, all right. So this picture pretty much looks like the same thing I'm doing here. If I have a mass and I'm pulling on it, there's my static friction force. I'm trying to break contact, okay. So this block isn't going to roll, okay, and this bowling ball is not going to roll, all right. So as it turns out, if you tried to pull the bowling ball, okay, to drag it, the static friction force is large, okay. So I keep pulling on it, okay, pulling on it, and eventually it gets to a point where contact's broken. Okay, but if I take that same bowling ball, okay, obviously without that attachment where I can attach the string, if I take the same bowling ball and just give it a little push right there, just a little push, okay, just a little quick push, okay. You can try this with any ball that you have in the house, okay. Just get a little push, okay, not on the carpet, okay, but on something hard, okay. So give it a little push. This thing's going to roll probably like 30 or 40 feet before it stops. Okay, so if that's the case, then the static friction force must be very small. Okay, so here the static friction force is large, okay, because it takes a lot of force to break contact. Here, you give this thing a push, and this thing's going to keep rolling and rolling and won't slow down for a long time. Okay, so it's two different situations. Okay, so here's the picture of the ball, a disc rolling down an incline. Okay, the incline was frictionless; it wouldn't rotate. So we know that there's friction. So here, I just drew a picture as this thing's rotating clockwise. Here's my axis of rotation, and my static friction force points backwards. That causes, okay, that clockwise rotation. That's the only force that acts, okay, that causes a torque, because right there, that's your moment arm, right? That's your moment arm. Okay, now, the odd thing is, okay, if we go back, okay, they have this picture in the book, okay? They have the ball rolling down an incline, which is perfectly fine. And you might draw this picture, okay, and notice, well, gee, the book never draws the picture, the force picture, when the ball is on the flat floor. Okay, why is that? Okay, the problem is if you draw this picture here, okay, you're going to get three different answers that don't make sense. Okay, so for example, if I look at this picture, okay, meaning I give this thing a small push, okay, so my finger's no longer touching it, and I draw the forces on the bowling ball. So I got the weight, I got the normal force, okay, and we had that static friction force, all right? So if I apply Newton's second law, net torque equals I alpha, all right? Well, we know from the picture, the static friction force, okay, exerts a torque, right? Because there's the moment arm. But Newton's second law says that if there's a torque, then there's an angular acceleration. So static friction exerts a clockwise torque, okay? So that means that this thing has an angular acceleration clockwise. So that says that if static friction produces a clockwise torque, then there'll be an angular acceleration, and that's going to cause the ball to rotate faster. But that doesn't make any sense, okay? Because you give the ball a little push, it's not going to start to speed up across the floor. Okay, we know it eventually stops. If you apply energy, okay, to the ball, all right, there's no energy loss due to friction, because remember, this is the energy loss due to kinetic friction, and we argued that when a ball rotates, right, we showed that when that part of the ball is about to hit that part of the ground, that those two meet and then no longer meet. That's a stationary point of contact. So it's not kinetic friction, okay? So where the ball touches the ground, okay, static friction, okay, static friction so static friction is a non-conservative force, but it doesn't do work because that static friction force doesn't act over any displacement. That's a stationary point of contact. So there's no work done by there's no work done by static friction. There's no energy lost due to kinetic friction because there's not kinetic friction in the problem. So energy is conserved. Okay, so forget about potential energy because it's gone a flat floor. So if energy is conserved, that says K initial equals K final. So that says that this thing is going to roll with constant speed forever. Okay, but analysis number one says it goes faster and faster. Okay, analysis number two says it goes with constant speed of the center of mass. Okay, if I use Newton's law, okay, to analyze the picture, okay, Newton's second law, so net force equal ma center of mass in the x direction. The only force I have on this thing in the x direction is static friction. Okay, so I have a regular coordinate system. Okay, so if I do F equal ma in the x direction, I have minus static friction equals ma. Okay, so if I solve this for a center of mass, okay, that says that the acceleration is negative. That says the ball slows down. Okay, so that's one of the reasons why you see this picture, okay, in the chapter. That's no big deal. Obviously, the ball's rolling downhill. It's going to go faster, okay? But you never see this picture drawn because if you apply torque, it tells you the ball's speeding up. Apply energy, it tells you the center of the mass of the ball is going at constant speed. If you apply Newton's second law with force, it tells you the ball slows down, okay? So you get 3 different results, okay? So, and the book really doesn't go into the minutiae of that, so it totally ignores it, okay? So what's really going on is we assume all the objects in this course are rigid, okay? Meaning they don't really deform as they roll, okay? But bodies are not perfectly rigid. Like if you roll like a basketball or a tennis ball across the floor, there's some deformation to some extent. So here's kind of an exaggerated picture of something rolling, okay? So as the ball, okay, as this part of the ball approaches the floor, okay, essentially it makes a collision with the floor, okay? So the collision forces in the front of the ball are a little bit bigger than the collision forces toward the back, okay? So as the ball rolls on the floor, that normal force, okay, is not really just one arrow, okay? It acts over that region. And when the ball rolls and hits the floor there, okay, that collision, these collision forces are larger than the ones in the back. And what that results in is you have normal forces toward the front are a little bit bigger than normal forces toward the back. So the effective normal force is more on that side, okay? So I drew the normal force more on that side, okay? And it kind of acts in front of the axis of rotation, so that would cause a counterclockwise torque, okay? So that would account for why the thing eventually slows down, all right? So that's why that picture gives you 3 different answers, because we're assuming the normal force acted right through the center of mass and didn't exert a torque, okay? So don't worry about this, okay? Don't worry about that. I just threw that in because if you try to draw that picture, okay, you're going to get a nonsense result. And it's not obvious why you get a nonsense result. So I have 2 inclines, both the same angle, both the same length. The object's going to go down. One is frictionless, okay, and one is not frictionless. Okay, this one here is rough. So here I have a glider, like on an air track, and here I'm going to roll a ball, and they both start from rest. Okay, which one reaches the bottom first? All right, who wins? Well, we know from the earlier chapters that the acceleration of the glider is g sine. Okay, so what is the ball doing that the glider isn't? Okay, well, the ball has to rotate. And so some of this potential energy, some of that mgh potential energy gets wrapped up into rotating. So the glider doesn't have to rotate. So all of this potential energy up here gets converted into straight line 1/2 mv squared kinetic energy. Okay, so the glider is going to win. Okay, winner, winner, chicken dinner. Okay, so we're going to calculate, I think there's a homework problem that asks you to find the acceleration of the center of mass of the rolling object. So this is similar to the picture we drew previously. Okay, so I have a solid, uniform, round object. Okay, this could be a disc or it could be a solid sphere. It doesn't have to be solid, but let's say it's a disc rolling down the incline, and I want to calculate the acceleration center of mass. So I'm kind of doing the 5-step method. My picture, I have my forces, okay, but I have to be really careful how I draw my forces. So there's my mg, there's my normal force, okay, there's my static friction force, okay, so picture forces, coordinate system, acceleration's down, so that's the direction of my x-axis, okay. I broke up my mg, okay, so I'm going to throw mg away. I have mg cosine, mg sine, okay, and then I'm just going to apply F equal ma in my x direction because acceleration center mass in the x direction, okay. Okay, so when I do that, I look at the picture, I have mg sine points down, static friction points back. That's equal to ma, okay. Now, the problem is, I'm trying to find A, problem is I don't know static friction, okay. Now, what we have to be careful is, all right, we can't assume that static friction is at its maximum, okay. We can't assume that this thing is on the verge of slipping, all right. So I'll show you a video where I can have many different angles for which this thing will roll without slipping, Okay, so without any other given information, we can assume that this thing's about to slip. Okay, so static friction is not necessarily at its maximum. So that means we have to find static friction. Okay, so instead of applying F equal ma, I'm going to apply F equal ma in rotational form. Okay, about axis A. There's my axis A. Okay, so just look at, since my picture is drawn pretty clearly, I can easily see the only force that causes a torque is static friction, because all the other ones pass through the axis of rotation. Okay, and the good thing about circles is the radius, okay, is your moment arm. Okay, so the torque about axis A. Oh, and then I know that this thing is rolling faster clockwise. Okay, so clockwise is my positive direction for alpha, right? And that's where I said the book will solve all problems where that way is positive. Okay, and that's just a horrible convention, right? You wouldn't want to choose alpha to be negative, okay, for something that's spinning faster. Okay, I mean, you can do that, it's fine, but this is not good practice. Okay, so my net torque about axis A is static friction times the moment arm, that's equal to I alpha. Okay, so I'm trying to find static friction. Now I have an alpha I don't want, okay? But for something that rolls, okay, for rolling, acceleration of center of mass is equal to R alpha. So I can solve this for alpha, okay? And I can take that alpha, stick it right there, okay? So static friction times R is I alpha, okay? And then you gotta be careful in this chapter. Don't cancel the R's. That R comes down and it's squared, okay? Now I can take this static friction, okay? I can take this static friction here and stick it right there, okay? So equation number one. So here's equation number one, okay? I just rewrote right there, okay? So I have mg sine, minus static friction. That whole thing right there is static friction, all right? And then I just did the algebra and solved it for A, okay? Okay, so that says that the acceleration of the center of mass, okay, depends on the moment of inertia, okay? And remember, we saw that for these round objects, the moment of inertia about the center of mass goes as some constant times mr squared. So if I put in, okay, for the moment of inertia, okay, I put in what I is, okay, remember you get to say what I is in this class, so k mr squared, okay, so I get the acceleration of the center of mass, I got g sine on the top, and on the bottom I have 1 plus k, okay, so the acceleration of the center of mass just depends on that coefficient, right? We already know the coefficients of the hoop, disk, and sphere. So here, all three of them are lined up for the race. Now, if I just had a point particle, okay, or a block, okay, and it was frictionless, okay, then it wouldn't rotate. So I wouldn't have a moment of inertia, okay, the moment of inertia would be 0, and then this would reduce to, right, so I would be 0, okay, and then I would just have a 1 in the denominator, and then my acceleration would be g sine theta. So that was, again, one way to check to see if that answer could possibly make sense. You check it for the units, okay, the units and dimensions are correct, and then you check to see if it reduces to what you expect in the limit where these objects don't rotate, they just become the glider. Okay, so the glider on a frictionless track wouldn't rotate, so moment inertia is 0, it's acting as a point particle, and I get g sine just as we expect. Okay, so for the race, okay, they're all at the same spot, and for each one, for the hoop, disk, and sphere, I put in, okay, the moment inertia about axis A. So for the hoop, okay, that's mr squared, okay, so the mr squareds cancel, careful, I have 1 plus 1 on the bottom, so I have a 2 on the bottom. I do the same for the disk, okay, there's my half for the disk, so on the bottom I have 1 plus a half, so I have 3 halves on the bottom, that flips becomes 2/3. And then here I did it for the sphere, remember that's the other one we have to know, the 2/5. So I gotta be careful, on the bottom I have 1 plus 2/5, okay, so 5/5 That's 7/5, but it's in the denominator, and you flip it over, okay, and that's where the 5/7 comes from. And then I just converted each of these to a decimal, and then this shows you that before, when we argued that the sphere wins because most of its kinetic energy was wrapped up into translation, okay, here this shows that the acceleration of the center mass is 71% g sine, whereas the hoop is only 50% g sine. Okay, so that'd be another way to argue that the sphere wins. All right, so here's a problem where I have a disk, okay, and I'm going to have it roll without slipping down an incline, okay, and I want to find what's the smoothest that incline can be. What's the minimum value of the coefficient of static friction so that this disk can still roll without slipping, okay? So let's say I have this at some angle and it rolls, okay, and I want to make this as smooth as possible, okay? What's the smoothest it can be to where it's going to start to slip? Okay, so I want to find that coefficient of static friction, its minimum value. Well, that means, like I said here, it's about to slip. So at least then I can say the static friction is equal to mu times the normal force. Okay, when it's on the verge of slipping, that's when static friction is equal to mu n. Okay, so I'm trying to find mu, and the mu is wrapped up in the static friction, and static friction is wrapped up into the concept of torque. So because when I look at my force picture, okay, the only thing I did here to make life easy, okay, instead of drawing mg, I just drew the components. Okay, it just makes the picture much less messy. Okay, so again, the same picture we had before, right? This thing's spinning faster clockwise. That's my positive direction for alpha. The only force that causes a torque, okay, is static friction. All right. So again, torque is force times moment arm. Okay, so my torque about axis A. Okay, so remember you have to write the torque and moment inertia with respect to an axis. So static friction times the moment arm. Okay, remember the moment arm for the round disk is r, and it's a disk, so 1/2 mr squared. Okay, and then I'm trying to find mu, which is wrapped up into that, but now I have an alpha I don't want. Okay, so the pattern in these chapters, how do I get rid of the alpha? I say, okay, it's rolling, so A center mass is r alpha. Okay, so I solve this for alpha, and then right here I have alpha, I put in A center of mass over r. All right, so let's see, the r's cancel, so careful the algebra. Yeah, all the r's cancel, and I'm just left with 1/2 ma center of mass. Okay, now if I go back to the previous page, the acceleration of center mass for a disk was 2/3 g sine theta. So that's what I put right there for the acceleration of center of mass. I put 2/3 g sine theta. So static friction, okay, static friction is 1/2 m, and then A center of mass is my 2/3 g sine theta. Okay, so the 2's cancel, all right, and that gives me my static friction, right? But I know that static friction is equal to mu n, okay? And then I could just look at the picture and see that normal force is mg cosine, okay? So here's my static friction, okay? Static friction is this, my 1/3 mg sine, so I wrote 1/3 mg sine. And that's equal to mu times n, and my n is mg cosine. So the mg's go away, and I solve that for mu, and I get 1/3 tan theta. So as an example, if that incline was at 45 degrees, right, tangent 45 degrees is 1, then that's the minimum value of the coefficient of static friction, okay? So it can be rough, and it'll roll, okay? It can be that smooth, but if I sand it down and make it smoother, if static friction is 0.31, then the disk would slip.